Hello everyone, welcome to this video which is titled Neural Network from Scratch, a Masterclass. In this video, our main goal would be to design an entire neural network directly from the very basics, and then simultaneously we will also code it out from Python. We will not use a single advanced neural network or machine learning library such as TensorFlow, PyTorch. We will not be using these libraries. We will be coding everything ourselves from scratch. If you want to have a much better understanding or a much detailed understanding of every single aspect of what we are going to cover today, please refer to my Neural Networks from Scratch series, which has 28 or 29 videos currently. However, this video is meant for students who want to look at the from scratch implementation within 45 minutes to 1 hour. So, my name is Dr. Raj Dandekar. I graduated with a PhD in machine learning from the Massachusetts Institute of Technology. Before that, I did my bachelor's in mechanical engineering from IIT Madras. And since 2022, I've been working with Vizuara AI Labs. So, let's get started with today's masterclass. I've divided today's masterclass into four steps or four main subparts. We'll start out with the description of the problem which we are going to solve with the neural network. Then we will jump into the key building blocks of neural networks such as layers, activation, and loss. We'll look at the forward pass and the backward pass for each of these components. Then we'll be going into the third step, which is the optimizers, and integrating an optimizer with the forward and the backward pass. And finally, in the fourth step, we'll train the entire neural network in Python and we will visualize the results. So let's get started with step one, which is the problem description. So here's the problem which we are going to solve today. This is the data set which has been available to us or which we are going to consider today. You will see that every data point has two attributes, x1 and x2. Along with that, every data point which has been shown here belongs to either one of three classes, red, green, or blue. So I'm just writing that here. Every data point belongs to either one of the three classes, red, green, or blue. For example, this point right here belongs to the red class, whereas this point right here belongs to the blue class. Our main task is to develop a neural network which solves this classification problem. That means our main task is to develop a neural network or to train a neural network so that when any new data point is given to the neural network, it will correctly classify that point as either red, green, or blue. In this video, our main focus will be on training. I'll make a separate video later for testing on data which has not been seen before. That's the first step. This is the problem which we are going to solve. In the broad class of machine learning problems, this falls under the category of a classification problem because we are going to classify the data set into either one of the three types, red, green, or blue. Let's move to step 2 now. In step 2, we will be constructing the neural network architecture and we will code it out in Python. Before that, let me just code out the first part of the uh, this video, which is the problem description in Python. As I mentioned, whenever we cover one step, directly we will go to Python and we'll code it out. So this is the neural network from scratch masterclass Jupyter notebook. I'll be sharing this notebook with you uh, in the information section of this video. The first step is to load the dataset. So I'm going to be using a library which is called NNFS just because it contains a dataset called as spiral data. And then I'm going to run this part. So here you can see that the dataset has been loaded and I'm just going to plot the dataset using these set of commands. Matplotlib is one Python library which I'll be using for plotting. So here you can see that I've plotted these points. I've plotted 100 points here, and these are the true classification classes for these points. They belong to either of the three classes, red, green, or blue. So this is the data set which we have right now. That concludes the first step. Then let's move to the second step, which is understanding the layers, the activation function, and the loss. These three components, the layers, the activation function, and the loss, form the main heart or form the main core of the neural network architecture. And it's very important that we understand these three building blocks very clearly. So for each of these three building blocks, we'll be incorporating or we'll be implementing something which is called as a forward pass, and we'll be implementing something called as a backward pass. So for example, for the layers building block, we'll do a forward pass and a backward pass. For the activation function building block, we'll do a forward pass and the backward pass. And for the loss building block, we'll do a forward pass and a backward pass. Right now, if you don't know what is meant by forward or backward pass, it's totally fine. I intend to explain all of these aspects to you as the lecture proceeds. So let's start with the first uh, component of this architecture, which are the layers. So if you think of the neural network architecture, layers are the one which take up most of the space or form most of the key components inside a neural network. So this is how a neural network architecture actually looks like. If you scan it from the left to the right, from the leftmost side, we have to mention the inputs. So remember, every data point which we are considering over here has two attributes, x1 and x2, right? So we have two inputs. So remember, there is a data point here, and that data point is fed to the neural network, and the output of the neural network is classifying it into one of the three classes, red, green, or blue. That data point has two attributes, x1 is the first attribute, x2 is the second attribute. What happens after the input layer? So this is called as the input layer. What happens after the input layer is that we add additional layers which are called as the hidden layers. So for example, here you can see that the layer which I have represented by pink is the hidden layer 1, and the layer which has been represented by green is the hidden layer 2. I have marked them by layer 1 and layer 2 here. Each of the layer consists of what are called as neurons. So here you can see that the first hidden layer has 1, 2, and 3 neurons, and the second hidden layer also has 1, 2, and 3 neurons. Just like how cells are the fundamental unit of human life, neurons are the most basic fundamental unit of a neural network architecture. The computations of a neuron are the most fundamental step. Neurons add up together to form one layer, and layers add up or layers stack up to form multiple hidden layers. So here there are two layers. Then the output of the last layer is fed into the loss function. So there is an output which the neural network predicts. So there are three neurons here. And why three? Because we are going to make a prediction either red, green, or blue. So just for the sake of intuition, if the prediction comes out to be zero point 0.9, zero point 0.1, and 0, it means that for this data point which was considered, there is a 90% probability that it belongs to the red class, 10% that it belongs to the green, and 0% that it belongs to the blue, as predicted by our neural network. And then we'll need to compare how close is it with our actual data. So if the actual data is that this is a red point, we'll need to find the loss, and then there is a loss component at the last step or at the rightmost part of the neural network. So these are the key components of the neural network architecture. There are neurons, there is one layer, and when layers stack up, they form multiple hidden layers, and then there is a loss function towards the end. Let us look at each of these layers separately. If you look at the layer number 1, let's analyze this first neuron. If you look at the first neuron in the layer number 1, there are two lines which are connecting it to the inputs. There is one line which connects it to the first input, and there is second line which connects it to the second input. So there are something called as weights which are associated with every input. So for example, uh, consider the first neuron and its connection with the first input. There is a weight which is called as W11 here, that signifies the importance of how useful or how important that input is. And let's look at the second connection of the first neuron to the second input. The weight associated with that is W12. So the first neuron has two weights. both connect to the two inputs. Similarly, the second neuron will have two weights which are called as W21 and W22, and the third neuron will have two weights, W31 and W32. So these weights are represented in a matrix formula here. If you look at the first column of this matrix, that's W11 and W12, those are the two weights corresponding to the first neuron. Then in the second column we have W21 and W22, those are the two weights corresponding to the second neuron. And in the third column we have W31 and W32, those are the two weights which are corresponding with the third neuron. This is called as the weight matrix. These weights are the flexible parameters, or these weights are the connections in the neural networks whose value we don't know yet. We do not know how much importance does neuron 1 give to x1 and how much importance does it give to x2. How much importance does neuron 3 give to x1 and x2? We do not know this. So whenever a layer is created, these weights are initialized randomly, and our main goal as we train the neural network is to optimize these weights so that the loss is reduced. Remember that every neuron has also a bias associated with it. So this neuron, along with weights, it has one more parameter which it takes in, and it's called as bias. I'm representing it by B1. Similarly, the second neuron also has a bias term associated with it, and a third neuron also has the bias term, that is B3. So if you consider just the first layer, there are 6 weights and there are 3 biases. Now let's move to the second layer. In the second layer, if you consider every neuron, so let's consider this neuron here, which I'm marking with an arrow. This neuron has 3 weights associated with it. Remember, the outputs of the first layer, which are 3 outputs, will now be the inputs to the second layer. So this first neuron has 3 weights, each corresponding to the input which it receives. And those will be W11 star, W12 star, and W13 star. Similarly, the second neuron over here has 3 weights associated with it, W21 star, W22 star, and W32 star. And the third neuron over here also has 3 weights associated with it, W31 star, W32 star, and W33 star. Similar to the neurons in layer 1, the neurons in layer 2 also have a bias term associated with them. So the first neuron has a bias term B1 star, the second neuron has the bias term B2 star, and the third neuron has the bias term B3 star. All of these are the parameters of our neural network. So if you count these parameters in the first layer, we have 6 plus 3, which are 9 total parameters in the first layer. And if you count in the second layer, we have 9 plus 3, so there are 12 parameters in the second layer. If you add the number of parameters, we'll see that our neural network architecture has 21 parameters in total, whose value we do not know and whose value needs to be optimized, whose value needs to be found out. So let's say if you have a bunch of points, right? Let's say if you have a bunch of points like this and you want to find the perfect straight line uh, which goes through all these points. Initially you might start out with a bad prediction, and then you will improve, and then ultimately you will find the straight line which goes through all the points. And the parameters of this straight line will be a slope. The parameters of this straight line will be the slope and the offset. So there are two parameters here which we need to optimize. But in the case of neural network, you can think of it as a much more complicated and an expressive function than just a straight line. And so we have 21 parameters in total which really need to be optimized. So this is the neural network architecture and how it looks like. Remember that neurons are the most fundamental layer, or the most fundamental building block. Neurons assemble together to form one layer. Multiple layers stack up together to form a stack of hidden layers, and then we have a loss function towards the end. Now, as I mentioned, every component over here, layers, activation function, and loss, will have a forward pass and a backward pass. So let me explain. Let me explain to you what that actually means. So whenever you receive an input, so let's say whenever a data point is received, x1 or x2, some computations need to happen, right? Some computations need to happen in the layer 1. Then the layer 1 output is the input to the layer 2, and then the layer 2 output is, let's say, zero point 0.9, 0.1, and 0. So some computations need to happen. And when you give an input and a computation happens, and we have the predictions like this, and then a loss is found, that's called as the forward pass. So let's look at the forward pass through each layer for now. When we look at the forward pass, we'll be looking at three different things. We'll be looking at the computations performed by one single neuron. Then we will look at the output, which is given by a layer of neurons. And then we'll look at the output, which is given by a batch of data and layer of neurons. So remember that currently I just showed one data point, right? But we'll probably take 80 or 100 data points as input, and that's a batch of data. And even for the batch of data, we need the outputs coming from the final layer. So if we have a batch of 100 data, we'll have three outputs from the final layer, one output or three outputs for each data. So we'll need to also do the computation for batch of data. Let's first start with the computations for a single neuron. So you might be curious about what is the real computation which a neuron is performing. So when you think of a neuron, as you saw here, the neuron has, every neuron has inputs, and there are weights which are associated with inputs. So let's say that we consider this neuron over here. The inputs to this neuron are x1 and x2. The weights are w1 and w2, and every neuron also has a bias term which is b. And with these parameters, the output of a neuron is given by w1 into x1 plus w2 into x2 plus b. So you take the product of the input and weights, you add these. So this is the product of the first input and first weight. You add it to the product of the second input and second weight, and then you add the bias term to it. That's the output of one neuron. Remember, this operation which I'm showing you right here is the most basic mathematical operation performed in a neural network. This can also be represented in a matrix formula. If W is written as a vector like this, which is W1 and W2, if X is written as a vector which is X1 and X2, this output which I have mentioned here can also be written as the dot product between X and W, and we add it with B. In Python, this will be np dot dot x comma w plus b. That's the output of one single neuron. When bunch of neurons are combined together, it forms a layer. So let's say we have two neurons in this layer, and the first neuron has weights w11 and w12. The second neuron has weights w21 and w22. The output from the first neuron is output 1, the output from the second neuron is output 2. The bias associated with the first neuron is b1, and the bias associated with the second neuron is b2. So if you represent all of these in matrix formula, the weight matrix W can be represented by this formula. W is equal to, so if you look at the column of this matrix, it will correspond with, let me mark it with a different color. If you look at the column of this matrix, it will correspond with, if you look at the first column, it will correspond with the weights of the first neuron, and if you look at the second column, it will correspond with the weights of the second neuron. Remember, this is the notation which we will be following throughout this lecture. The columns of the weight matrix represent all the weights associated with one neuron. So the first column represents the weights of the first neuron, the second column represents the weights of the second neuron. If you make a mistake in writing the W matrix, the dimensions won't work out. So this is the W matrix, and the X matrix can be written like x1 and x2, where x1 is the first attribute and x2 is the second attribute of one data point. And the bias are b1 and b2. So like what we saw before, the output from the first neuron will be w11x1, uh, w11x1 plus w12x2 plus b1. The output of the second neuron will be w21x1 plus w22x2 plus b2. This again can be written in a matrix formula as np dot dot x comma w plus b. Now I want you to focus on this formula, the dot product of x and w plus b. You can see that this is the same as what we had written with just one neuron. So look at this formula for one neuron showing with an arrow here, and compare it with the formula for a bunch of neurons. It's the same. This is the advantage of representing parameters using matrices. because it just makes life very easy. It makes computations very, very easy. So you can use this same formula for computing the output from any number of neurons. Even if you have 50 neurons here, you just need three matrices. You need the input matrix, you need the weight matrix, and you need the bias matrix. Remember that for this formula to work, the weight matrix should be arranged like what I've shown here. The columns should represent the weights corresponding to each neuron. And now I want to take the final case where we have a batch of data. So let's look at this schematic over here. Up till now we only saw one input data, right? But eventually we'll have 50 to 100 data points, and we'll need to train the neural network or find the output for all of these data points. So for example, let's say the orange one here is my batch 1, and I want to find the output whether it belongs to red, green, or blue. Then I will input batch 2. I will want to find the output whether it belongs to red, green, or blue. And then I will input the batch 3, and again I want to find the output. So does that mean that do we need to compute this thing three times now because there are three input data? Let's find out. So very similar to what we did previously, we'll represent this in matrix notation. The W matrix will remain the same. So remember that even if the data are coming in multiple batches, the weight matrices are the same. We'll ultimately need to optimize the final values of the weights and biases, which will work for all the sets of data which are coming in. So the weight matrix, again, if you look at the column W11 and W12, which are the weights associated with the first neuron, and if you look at the second column, it's W21 and W22, which are the weights associated with the second neuron, and the bias term is B1 and B2. The input data is represented again in the matrix form. So the first row is the first batch of data x1, x2, which has been shown in orange color here. The second row is the second batch, which is shown in green color, and the third row is the third batch x1 and x2, which has been shown in the pink or the red color. Now, for each of these batch, there will be output 1 from first neuron and output 2 from the second neuron. So the output matrix will look something like this. It will have three rows. The first row will contain the output of the first neuron and the output of the second neuron for the first batch of data. The second row will contain the output of the first neuron and the output of the second neuron for the second batch of data. And the third row will consist of the output of the first neuron and the output of the second neuron for the third batch of data. So the dimensions here will be three row and two column. And again, the same formula works out. So if you do the dot product of x with w, first you can make sure that the dimensions make sense. The columns of x are the same as the rows of w. So we can take the dot product of x and w and then add b. Remember in Python, when we say np dot dot of two matrices, it just multiplies those two matrices. I want you to pause here and appreciate the beauty of this formula np dot dot x comma w. I'm just marking it with a star here. You can see that this same formula holds true for all these three cases. Even if we have one single neuron, even if we have a layer of neurons, or if we have a batch of input data with layer of neurons, this same formula works. And that's why I encourage all the students to use matrices when they start learning about the forward pass in the neural network. So now you are equipped that if you are given with even a batch of 100 data points and a layer of 50 or 100 neurons, using this same formula you will be able to find the output from the layer for all the batches of data. So for the first batch, there will be two outputs. From the second batch, there will be two outputs. And from the 100th batch, there will be two outputs. And all of that can be calculated by one single matrix representation. This is the master formula for calculating the forward pass from a layer in a neural network. So remember that every layer will have one output, right? Or every layer will have an output associated with each neuron. And this formula here np dot dot x comma w plus the bias will help you find that output. This is the forward pass through a layer. However, in neural networks, what is very important to do is also the backward pass. Why is the backward pass necessary? Because if you look at this weight matrix and the bias matrix, if you look at all of these 21 parameters here, we need to optimize these 21 parameters, right? which means that we need to find what are the best values of these 21 parameters which minimize the loss. So if the loss function looks like this, we want to find the minima of the loss, right? Let's say when we start out randomly, we are at some point here in the loss function. Ideally we want to keep moving in this direction so that we reach the minima, and this direction turns out to be the direction of the steepest descent, and the direction of the steepest descent is given by the negative of the gradient, or the negative of the partial derivative of the loss with respect to the parameter. So let's say we are starting out with some parameter w. Let's say we are in a layer and one parameter in that layer is w11. We start it out randomly. The next iteration of w11, we should move in the direction of w11 minus some step size multiplied by the partial derivative of loss with respect to w11. So this is the direction of the steepest descent, and we should start moving in this direction as the iterations proceed. This is exactly what we'll be doing in the optimization procedure. But for us to implement the optimization procedures such as gradient descent, etc., it is very important for us to find these gradient values. It is very important for us to find the partial derivative of the loss with respect to the weights, the biases, and the inputs of a neural network. So the way I think about the backward pass is that the backward pass is a method to find the partial derivative of the loss with respect to the weights, with respect to the biases, and with respect to the inputs of a layer. And why do we need these partial derivatives? We need these partial derivatives because let's say we find the loss in a particular iteration, and we want to find who to blame, which weight is to blame for this big loss, which bias is to blame for this big loss. So if you want to decide who to blame, we need to find out if a small change in that parameter leads to a big change in loss. For example, if a small change in w11 leads to a very big change in the loss or very big increase in the loss, maybe w11 is to blame for the large loss and I should reduce it, right? So to find these changes, we need to find how the loss depends on w11. That's why we need to find the partial derivative of loss with respect to the weights, with respect to the biases, and with respect to the inputs of a layer, so that we can update the weights and biases of the layer. um, okay, so for the purposes of the backward pass, I'm going to fix on one layer, and whatever we are going to discuss right now will hold true for all the layers which we consider in the neural network. So this is the neural network, this is the input layer. But for the purposes of this section, which is the backward pass, I am going to look at this layer, which is the second layer. And I want to find the partial derivative of the loss with respect to all the weights in this region, all the biases in this region, and also the in this layer, and also the inputs to this layer. So the outputs of the first layer are x1, x2, and x3. Those are the inputs to this layer. The weights of the first neuron are W11, W12, W13. The bias is B1. Similarly for the second neuron and third neuron. So I want to find the partial derivative of the loss with respect to all these weights, all these biases, and these three inputs as well. So let me see how to do that. For that, we are going to use one of the fundamental rules of calculus, which is called as the chain rule. If you want a revision or a recap on the chain rule, I have a lecture in this series which is called Understanding Chain Rule, the Backbone of Neural Networks. I highly encourage you to go through that. Okay, so first let's see how to find the partial derivative of loss with respect to W11. If I want to find the partial derivative of loss with respect to W11, I have to go through this Z1. Z1 is the output of the first neuron. So this is how I will apply the chain rule. I will first find the partial derivative of loss with respect to Z1 and then multiply with the partial derivative of Z1 with respect to W11. So I'll find the partial derivative of loss with respect to Z1 and multiply with the partial derivative of Z1 with W11. Let's say this is given to us. Let's say the partial derivative of loss with respect to z1 is given to us. Then I just need to find the partial derivative of z1 with respect to w11, right? So how does z1 depend on w11? Z1 is w11 x1 plus w12 x2 plus w13 x3 plus b1. So partial derivative of z1 with respect to w11 is just x1. So it turns out that partial derivative of loss with respect to w11 is just x1. Similarly, partial derivative of loss with respect to w 12 will be x2, and partial derivative of loss with respect to w13 will be x3. That's the first intuition to develop. The partial derivative of loss with respect to the weights is equal to this first term, partial derivative of loss with respect to z1, z2 and z3, multiplied by the input which is associated with that weight. Now, when we are going to come to every such layer, we are going to assume that this partial derivative is given to us. Because remember, we are back propagating, so we are starting from the end. So whenever we reach one layer, we are going to assume that the partial derivative loss with respect to that layer output is given to us. So for example, if we reach this layer, the outputs of this layer are z1, z2 and z3. And we are going to assume that partial derivative of L with respect to z1, z2 and z3 is given to us, and that matrix we are going to call as dl dz matrix. Okay, so this is the computation of partial derivative of loss with respect to w11. To find the partial derivative of loss with respect to b1, we employ the same thing. We first find the partial derivative of loss with respect to z1 and then multiply with the partial derivative of z1 with respect to b1. And remember, z1 depends on b1 like this. So partial derivative of z1 with respect to b1 is just 1. So then partial derivative of loss with respect to b1 is just the partial derivative of loss with respect to z1, which is the output of that layer in that neuron. Now, why am I telling you to find the partial derivative of loss with respect to the layer inputs? The reason is because the partial derivative of loss with respect to the inputs of this layer will be the partial derivative of loss with respect to the outputs of the previous layer. So remember that there is another layer before this layer, and the output of this layer is x1, x2 and x3. And to find the partial derivative of loss with respect to the weights and biases of this layer, we will need the partial derivative of loss with respect to x1, x2 and x3. So that's why whenever we look at a layer, it's also very important to find the partial derivative of loss with respect to its inputs, because that will help us to find the gradients with respect to weights and biases of the previous layer. Remember that ultimately only weights and biases are going to be updated. So in that sense, we only need the gradients of the loss with respect to weights and bias. But to find the gradients of weights and bias with one layer, we need to find the gradient or we need to know the gradient of that layer output. Like for example, in this layer, we needed to know the partial derivative of loss with respect to outputs, right? And this output is the input to the next layer. So that's why when we look at every layer, we definitely need to find the partial derivative with the inputs, because it's this term which I am telling you to assume, because it's going to come from the layer after the layer which we are looking at right now. Okay, so to find the partial derivative of loss with respect to x1 is a bit tricky, because loss is a function of z1, z2 and z3, and even z2 and z3 are influenced by x1. So the chain rule here works out like this: partial derivative of loss with respect to x1 is partial derivative of loss with respect to z1 multiplied by z1 with x1 plus partial derivative of loss with respect to z2 multiplied by z2 with x1 and plus partial derivative of loss with z3 multiplied by z3 with x1. The reason it becomes like this is because z1, z2 and z3 all depend on x1. So partial derivative of loss with respect to x1 will be just this summation over here. I'm showing you these things just to build up your intuition to find the partial derivative of loss with respect to weights. The inputs come in the picture. To find the partial derivative of loss with respect to inputs, the weights come in the picture. To find the partial derivative of loss with respect to the biases, we just need the partial derivative of loss with respect to the layer outputs. Now let us see how this looks like in a matrix formula. There is a very simple matrix representation to find these partial derivatives whenever we look at a layer. So let's say W is this matrix. Again, the columns are the weights of one neuron. So there are three neurons here, right? So each column are the three weights associated with each neuron. X are the inputs, and again they will be in batch format. The first batch has inputs x1, x2, x3. Remember that this layer has three inputs because there are three outputs of the preceding layer. So from the first batch, the inputs are x1, x2, x3. From the second batch, the inputs are x1, x2, x3. And from the third batch, the inputs are x1, x2, x3. And then we have another matrix which is dl dz, which is the partial derivative of loss with respect to the layer outputs. And again we have three batches, right? So for the first batch, it's the first row. For the second batch is the second row, and for the third batch it's the third row. Remember, these values are given by the partial derivative of loss with respect to the inputs of the next layer, which we would have already computed before coming to this layer. Okay, now the first formula which I want like to tell you is that for any given layer, the partial derivative of loss with respect to the weights of that layer is given by this simple formula: x transpose multiplied by dl dz. And x is this, dl dz is this. This one formula gives us the partial derivative of loss with respect to all 9 weights over here. So this will be a 3 by 3 matrix. So for example, if you look at the first row and first column, it will give the partial derivative of loss with respect to w11. Similarly, there are 3 rows and 3 columns. As an intuition, what you developed here to find the partial derivative with respect to weights, inputs coming to the picture. That's why there is an x transpose here. Then for any layer, the partial derivative of the loss with respect to its biases is just given by summing the rows of dl dz. So for example, here dl dz is 3 by 3, right? If you just take row 1 plus row 2 plus row 3, it will be 1 row and 3 column. And that will be the partial derivative of loss with respect to the three biases, which is bias 1. So here it will be bias 1, bias 2 and bias 3. Remember that there are only three biases, so this will be 1 row and it will be 3 column. And then for any given layer, the partial derivative of the loss with respect to its inputs is given by this formula: dl dz multiplied by weight transpose. So dl dz is 3 row 3 column, and weights is also 3 row 3 column. So again this will be 3 rows, this will be 3 row and 3 column. The first row will give the partial derivatives with respect to first input batch, second row with respect to second input batch, and third row with respect to third input batch. Again, the intuition which we developed over here, to find the partial derivative of loss with respect to the inputs, we need to take the weights into account. That's why to find the partial derivative of the loss with respect to input of a layer, we use this formula: dl dz multiplied by the weight transpose. So remember that whenever any layer is given to you, first using this formula np dot x comma w plus b, you do the forward pass. And remember that when you do the backward pass, you need to store three values. You need to store the partial derivative of the loss with respect to the weights of the layer, which is given by x transpose dl dz. Then you need to store the partial derivative of the loss with respect to the biases of that layer, which is given by this formula summing the rows of dl dz. And you also need to store the partial derivative of the loss with respect to inputs of that layer, which is given by this formula dl dz multiplied by the weight transpose. Now we are ready with the understanding of how the forward pass and the backward pass is implemented for a layer. So let's look at the code. Okay, so we will be creating a class called layer dense. What this class will be doing is that it will first have an init method, which will be for initializing the weights and the biases to some random values. Then it will have the forward method, and it will have the backward method. So if you look at the init method over here, the whenever an instance of the class is created, we need to pass two attributes: the number of inputs and the number of neurons, right? So first the weight matrix will be created. Remember, the rows will be the number of inputs and the columns will be the number of neurons. So every column will have weights corresponding to that neuron. So we are going to initialize them randomly through a Gaussian distribution, and the biases we are going to initialize to 0 for all the neurons when we start it out, or when we start the training. The weights will be initialized to random Gaussian values and the biases will be initialized to 0. That's the init method. When we come to the next method, which is the forward pass, this is called as the forward method. And as I said, the formula which we are going to use is, let me again show it to you on the whiteboard. The formula is np dot dot x comma w plus b. So in the forward pass, the output is np dot dot inputs comma self dot weights plus self dot biases, which is np dot dot x comma w plus b. That's it. And when we look at the backward method now, we are going to store three things as I mentioned. First, we are going to store the partial derivative of the loss with respect to the weights, and this is given by the formula x transpose dl dz, which has been mentioned over here. X transpose dl dz. So dl dz is stored in this d values. Remember, this backward method takes in an argument. It takes in d values, and d values is the partial derivative of the loss with respect to layer outputs. So that is already given to us. Then to find the partial derivative of the loss with respect to the biases, we just take the d values, which is the dl dz matrix, and we sum the rows. In Python, when we want to sum the rows of a matrix, we do np.sum, the matrix name, and axis equal to 0. Remember, we are going to keep dims equal to true, because if we don't use keep dims equal to true, the result will be a one dimensional matrix, but we want it to be two dimensional ideally. So everywhere where we are going to do np.sum in this code, we will use keep dims equal to true to retain the two dimensional nature of the matrix. And then we are also going to find the partial derivative of the loss with respect to the inputs, right? And that is given by this formula, which is dl dz multiplied by the weight transpose. uh, so I'm just marking it with an arrow here, dl dz multiplied by the weight transpose, and that is exactly what we will be writing it in the code. That will be np dot dot dl dz multiplied by weight transpose. Remember, in Python, when we do np dot dot, it is just taking the dot product of the two matrices. So this is how the layer dense class is coded. And as you can see, if you understand the basic mathematics behind the forward pass and the backward pass, it's very easy for you to understand how we write the layer dense class. So the coding is not the very hard part of it. The hard part is actually understanding how these matrix multiplications come into the picture, how these formulas are derived. If you want to go into a lot of detail in each of these things, I have made separate lectures in the neural network from scratch series, and I highly encourage you to check it out. After covering the first section, in the second step, so let me remind you of the second step. In the second step, we had layers, activation, and the loss. We looked at the first step, which is layers, the forward pass and the backward pass, and how to create the layer dense class. Now we'll look at the second step, which is the activation functions. Activation functions really make neural networks very expressive. If we did not have activation functions, for example, then the neural networks would be as expressive as a straight line. So if you had a very complicated underlying function, let's say for example, if you have the underlying data which represents a sinusoidal curve, something like this, and you did not have activation functions in the neural network, it turns out that the neural network is just good to approximate straight lines, and it cannot even capture the rises and the fall in the underlying data. Activation functions make neural networks expressive. It teaches the neural networks to be powerful enough to capture any difficulty or any complexity in the underlying function. In our case, for example, we need to classify the points into red, green, or blue, right? And the underlying function which helps us do that might not be very simple. So just having a linear line or a straight line will not help at all. We need activation functions to make the neural network more expressive, so that it can do a good job at this classification task. There are a large number of activation functions such as tanh, sigmoid, ReLU, softmax, swish, leaky ReLU, etc. In the neural network from scratch series, there is a separate lecture on coding all of these in Python. In this lecture, I am only going to go through those activation functions which are going to be needed for us. So since this is a classification task, we definitely need the softmax activation layer at the output. And after the first layer, we are going to use a very traditional and commonly used activation function, which is the ReLU activation function. The place where activation functions are used is that if you look at the output of these neurons, the output will be a w11x1 plus w12x2 plus b, right? This is where the ReLU activation function is applied. So when we come to the next layer, w11x1 plus w12x2 plus b is not the input to the next layer. Rather, the input to the next layer is ReLU of w11x1 plus w12x2 plus b. That's the input to the next layer. So outputs from all the neurons of the first layer go through the ReLU, which then serve as the inputs to the second layer. Similarly, outputs of all the neurons in the second layer go through the softmax activation function. And then that leads to the point 0.9, point 0.1, and 0 predictions which we mentioned about earlier in this video. So after every layer, activation functions are generally used. Now let us try to understand both the ReLU and the softmax activation. Similar to layers, we'll need to define a forward pass and a backward pass even for activation functions. For the forward pass, we'll just need to understand how the activation function works. For the backward pass, we'll need to work with derivatives. So let's get started with the ReLU activation function and looking at its forward and the backward pass. The ReLU function typically takes an input and returns an output. So if the input is x and the output is z, z is related to x like z is ReLU of x, and the function is maximum of 0 comma x. What this means is that if x is greater than 0, the output of the ReLU is just equal to x. But if x is less than 0, then the output of the ReLU will be 0. So if you see on the positive side, ReLU just behaves on like a straight line. But on the negative side, it's brought down to 0. And this simple non-linearity makes a huge difference. In fact, this sinusoidal function which I mentioned, it turns out that if we chain a bunch of ReLU activation functions together, we can capture this sinusoidal pattern. And that the reason for this is that we introduce a non-linearity because of this edge here. So there is a 0 flat and then there is an edge, so there is a non-linearity here. This is the ReLU activation function. It is clearly not differentiable at x equal to 0, but the addition of this non-linearity makes the neural network very expressive. So this is the forward pass. Whenever an input is given to the ReLU, using this graph here, it computes the output z. Now, what's the backward pass? So when we look at the ReLU, again, similar to the layers, we have received the partial derivative of the loss with respect to the layer output, right? Even when we look at the ReLU activation, the partial derivative of loss with respect to the ReLU output is given to us. And we will need to find the partial derivative of the loss with respect to the ReLU input. And to do that, we'll use the chain rule. So the partial derivative of the loss with respect to the ReLU input is the partial derivative of loss with respect to the ReLU output multiplied by the partial derivative of the ReLU output with ReLU input. So partial derivative of z with respect to x. Now to find this, let's look at the graph of the ReLU. If x is greater than 0, then z is equal to x, right? So this partial derivative will be equal to 1 if x is greater than 0. On the other hand, if x is less than or equal to 0, so if we are in this regime over here, so if we are in this regime, then x will be or z will be equal to 0. So the partial derivative of z will be with respect to x will be 0 if x is less than or equal to 0. This is how this particular term will operate. And the way we do it in practice is that what we'll do in Python is that to find the partial derivative of loss with respect to ReLU input, first we'll just set the answer to be partial derivative of loss with respect to ReLU output. Let's say the answer is equal to this. Then we will look for all the x where x is less than or equal to 0. And we'll find those indexes. We'll find those input indexes for which x is less than or equal to 0. And then for those indexes, we will set the corresponding entries in this matrix to be equal to 0. Because remember that only for those indexes we will multiply this matrix with 0. For all other indexes we will multiply this matrix by 1. So it can stay as it is. Only for those indexes where x is less than or equal to 0, or where the input is less than or equal to 0, we'll set the matrix to 0. So for example, if the dl dz matrix is this, um, 1 2 4 5 6 7, if this is the dldz matrix, and if x is equal to 1 minus 2 3 4 minus 3 and 6, if let's say this is my dldz matrix, and if this is my x, so then I will look at places where x is less than or equal to 0. So here x is less than or equal to 0, here x is less than or equal to 0. So the indexes are first row second column and second row second column. I'll find these indexes here and I'll set it equal to 0. So then my final answer would be 104 and 507. This is how we deal with the non-differentiable ReLU at x equal to 0. ReLU is not differentiable at x equal to 0. So Python, using this intelligent trick, Python distinguishes, or Python breaks it into two domains, x greater than 0 and x less than or equal to 0. And using this trick, we just set the corresponding entries to 0. And that's how we'll be doing the backward pass with ReLU. And now let us jump into Python code to understand the forward and the backward pass for ReLU. Okay, so for the forward pass ReLU, we'll take inputs as the argument, and the output will just be the maximum of 0 comma inputs. This means that if inputs are greater than or equal to 0, the output will just be equal to the inputs. But if input is less than or equal to 0, the output will be 0. That's exactly what we saw in this graph over here. Now for the backward pass, we have been given this d values, which is dl dz. As I mentioned on the whiteboard, first we will set the answer to be just equal to dl dz. Then we will look for the indexes where the input is less than or equal to 0, and then we'll set all those values to be equal to 0, and that's our answer. So this is how the forward pass and the backward pass are implemented for the ReLU activation function. We have a second activation function, which is the softmax, and let us see how the forward and the backward pass is implemented for the softmax activation function. This is how the softmax usually operates. We take in the inputs which are x1, x2 and x3. So let's say I have a point which has two attributes x1 and x2. We go through the first layer, we reach the final layer, and then the final layer gives me x1. Let me call it x1 dash, x2 dash and x3 dash. So then all of these will change here. Let me replace this with dash values. Okay, so then these are not directly fed to the loss. We have a softmax. The reason we have a softmax is, let's say this output is uh, 10, 2 and 1. Now ideally I want the output to be related to the value or the class which x1 or x1 x2 belongs to, right? So remember in this plot which we showed, x1 and x2, any given point belongs to either one class, red, green or blue. So this point which we have red, green or blue, right? So this point which we have looked at right now, which is x1 comma x2, belongs to either one class, red, green or blue, and I want my neural network prediction to give me that class. So right now it's looking like the class red has the value 10, class green has the value 2 and the class blue has the value of 1. This tells me that there is a higher chance of it being related to class red, right? But this is not in terms of probability. Ideally I want to make a statement that there is 90% chance that this point belongs to class 1, there is 10% chance that it belongs to class 2, and there is 0% chance that it belongs to class 3. So I want to convert these outputs into a set of probabilities. So there are few requirements for this. I want my outputs to lie between 0 and 1. I want my outputs to lie between 0 and 1 because I want my output to represent some probability, and these numbers are clearly not between 0 and 1. Secondly, I want the sum of all of my outputs. I want sum of all of my outputs to be equal to 1, because then they will be really related to probability, right? 90%, 10% and 0, this adds to 100%, which is good. But here these values just add up to 13, which makes no sense at all. So I want my output to lie between 0 and 1, and I want my outputs to sum up to 1. What's the function which does that? So there comes the softmax function. What the softmax actually does is that let's say we have x1 dash, x2 dash, and x3 dash, right? It gives three outputs, z1, z2, and z3. For z1, it uses e raised to x1 dash in the numerator and divides it with the summation of e raised to x1 dash plus e raised to x2 dash plus e raised to x3 dash. Similarly, for x2 dash as an input, it produces an output which is e raised to x2 dash divided by the summation of e raised to x1 dash plus e raised to x2 dash plus e raised to x3 dash. Similarly, for Z3, softmax does e raised to x3 dash divided by e raised to x1 dash plus e raised to x2 dash plus e raised to x3 dash. Now look at these three outputs, Z1, Z2, and Z3. First of all, in all of these, we'll see that the denominator is greater than the numerator. So the first conclusion from this is that Z1, Z2, Z3 definitely lie between 0 and 1. That's the first conclusion. The second conclusion, if you look at it closely, is that Z1 plus Z2 plus Z3, Z1 plus Z2 plus Z3 will be equal to 1. This is amazing because now they are directly related to probabilities. So my Z1 can be, this is just rough values, zero point 0.9 or point, Z2 will be zero point 0.1 and Z3 will be zero point 0, let's say. Then these are much closely related to probabilities, right? I can say that with I'm 90% sure that my point belongs to red, and I'm 10% sure that it belongs to green, and and it does not belong to, I'm 0% sure that it belongs to blue. And this is my neural network prediction. I'm much more comfortable with this prediction, and that's why for all classification tasks, softmax is used as the activation function, usually at the output layer. In all the preceding layers, generally ReLU is used. So this is what we'll be doing in the forward pass of the softmax activation function. Now let's look at the backward pass. So we have been given partial derivative of L with respect to Z1, Z2, and Z3, and we have to find the partial derivative of L with respect to x1, x2, and x3. So let's say partial derivative of L with respect to Z1 is given to us, and we want to find the partial derivative of L with respect to x1. Now this is a bit tricky because uh, x1 affects both z2 as well as z3. Um, so the partial derivative of L with respect to x1 is not just partial derivative of L with respect to z1 multiplied by partial derivative of z1 with respect to x1. We also need to add these terms which take into account the effect of x1 on z2 and the effect of x1 on z3. So remember, look at z1, z2, and z3. All of them have this x1 term, right, in the denominator. So x1 clearly has an impact on all three, z1, z2, as well as z3. So we need to take all of these additional terms into account. So this makes the backward pass for the softmax function very complex. So we'll not be implementing the direct backward pass for the softmax function. We'll be doing a trick. We'll be chaining the softmax with the loss, and then we will use a combined backward pass for the softmax as well as the loss. For now, it's very important that you just have a look at the softmax activation function forward pass, and I'll show you how the forward pass is implemented in Python. So here is the softmax activation function forward pass. We first look at all the values in the matrix and we take the exponents. Remember that we first subtract the maximum value from each row just to make sure that the values don't grow too much. And then we divide each value by the summation. So for example, if the inputs are, let's say if the inputs are 1, 2, 3, and 4, 5, 6, what we'll be first doing, as has been mentioned in the code, is that first we'll be subtracting from each row the maximum of that row. So from the first row we'll subtract 3, so this will be 3 minus 1 0, and this will be minus 2 minus 1 and 0. First row will be minus 2 minus 1 0, second row will be minus 2 minus 1 0. Then we will be doing the exponent operation. So let me rub this. Or let me write it over here. So then each of the entries will be doing the exponent operation. Okay. So then after we subtract the maximum value, Then we'll be, let's say, for the first entry, e raised to minus 2, e raised to minus 1, e raised to 0, e raised to minus 2, e raised to minus 1, e raised to 0. And then what we'll be doing is that we'll be taking the summation for each of these. So we'll do e raised to minus 2 divided by e raised to minus 2 plus e raised to minus 1 plus e raised to 0. And we'll be doing the same thing for all the entries in this matrix. So this is how we'll be uh, actually finding the softmax forward pass. Remember, each row in this matrix belongs to the batch. So the first row is the input to the softmax from the first batch. The second row is the input to the softmax from the second batch of the input data. So this is how the softmax activation function is implemented in the forward pass. We are not looking at the backward pass of the softmax because, as I mentioned, it gets a bit more complex, and we'll be chaining it with the loss function, and then we'll be calculating a combined backward pass for the softmax activation as well as the loss function. Now, let's look at the third step. So we have finished the first two steps in the, or we have finished the first two aspect of the second step, which are the layers and the activation function. And now we are ready to look at the final step or the final aspect of the second step, which is looking at the loss function. So whenever we have an input data, let's say it has two attributes x1 and x2, we get the prediction. As we saw, we get the softmax prediction, let's say zero point 0.9, zero point 0.1 and 0. So 90% confidence that it belongs to the red class, 10% confidence that it belongs to the green, and 0% confidence that it belongs to the blue. And let's say the true value is that this data point actually belongs to the red class. So let's say the true value is 1, 0 and 0. So now, to find the loss between these two, so the predicted values are zero point 0.9, zero point 0.1 and 0, and the true value is that it belongs to the red class, which is 1, 0 and 0. Now the question is, how do you find the loss function between this matrix and this, or this vector and this vector? It turns out that there is a simple formula for finding this loss, and it's called as the categorical cross entropy loss. This formula is very simple. You take the true values and you take the predicted values, and for all of these neurons you take a summation of the true value multiplied by the log of the predicted value, and then you add a negative sign. So for example, for this first neuron, the true value is 1, right? Because the correct value is 1. So it will be minus 1 into log of the predicted. So then it will be minus 1 into log of zero point 0.9, plus for the second neuron, the true value is 0 because the second neuron, because it's 100, plus 0 into log of zero point 0.1 plus 0 into log of 0. So to this whole thing will append this minus sign. So it will be minus of log 9 plus 0 into log of zero point 0.1 plus 0 into log of 0. So the actual answer will be negative of log of zero point 0.9. So this formula can actually be simplified to a much easier formula, and that is just taking the negative log of the correct label confidence. So the first step is to look at the correct label for the data. So for this data point, the correct label is the first one. Look at the confidence. So there is 90% confidence, and take the negative log of that. So it will be negative log of zero point 0.9. So the loss will be negative log of zero point 0.9. And let's see why this makes sense. Now if y1, which is the correct label, if this value was zero point 0.1, so if we only had 10% confidence in the correct label, the loss would be minus log of zero point 0.1, which will be a very high loss. Whereas if you are 100% confident that y1 is equal to 1, then the loss will be minus log of 1, which will be equal to 0, which means the loss is 0. That makes sense, right? Because the correct label was equal to red, and if we had 100% confidence in the correct label, which means that the loss should be equal to 0. That's why this categorical cross entropy loss intuitively makes sense, and you can see it from the log plot. So the negative log plot actually looks something like this. And So this is the negative log plot. This is x equal to 1. So we will always stay in this regime because our outputs are probabilities and they will never become greater than 1. So if the values are close to 1, then the loss will be very low. If the value is 1, then the loss will be 0. If the value is zero point 0.1, you will see that the loss is very high. And as the value gets close to 1, the loss will be lower and lower and lower. And why will the loss be 0 at 1? Because that's our true label, or that's the correct label. So here on the y-axis, I'm plotting negative log of x, and on the x-axis, I'm plotting x. So this is why the categorical cross entropy loss makes intuitive sense. Now I'll show you how to do a forward pass on the categorical cross entropy loss. So let's say we have three batches of input data. For the first batch, the output is zero point 0.7, zero point 0.1, and zero point 0.2. So this is from the first batch. From the second batch, the output of the final three neurons are zero point 0.1, zero point 0.5, and zero point 0.4. This is the second batch. And for the third batch, the output of the three neurons are 0 0.02, zero point 0.9, and 0.08. And for these three batches, so for the first batch, the true label is 100, which is red. For the second batch, the true label is green, which is 1010. And for the third batch also, the true label is green, which is 010. And now I want to find the loss, right? So as I mentioned, we'll do it batch by batch. For the first batch, we'll look at the correct label. The correct label is the first one. Then we'll take a negative log of the correct label confidence, which is negative log of zero point 0.7. Then for the second batch, we'll look at the correct label. The correct label is 2, which is green. We'll look at the correct label confidence, which is zero point 0.5, and then we'll do negative log of zero point 0.5. For the third batch, we'll look at the correct label. Again, it's 2 because the answer is green. And we'll look at the um, correct label confidence, which is zero point 0.9, and then we'll do negative log of zero point 0.9. So the loss from these three batches is minus log zero point 0.7, minus log zero point 0.5, and minus log zero point 0.9. And to find the mean of this loss, we'll just be taking an average. So 1 by 3 log of zero point 0.7 plus log of zero point 0.5 plus log of zero point 0.9. So the mean loss will be 0.385. This is how the loss is categorical cross entropy loss is calculated in the forward pass. Now we do one more thing in the code. If the input is one hot encoded, then how to do it in the code? That's what I'll be showing you. So let's say this is the predicted values, right? And these are the input values. And these are one hot encoded values, which means that for the first batch of data, which is the first row, the correct answer is red, so it's 100. For the second batch of data, the correct answer is green, so it's 010. And for the third batch of data, the correct answer is green, it's 010. Now from this input matrix, and from the predicted, how do we get to this loss minus log zero point 0.7, minus log zero point 0.5, and minus log zero point 0.9 in a code manner? So right now, I just told you to look at the correct class, right? But how to do it in code? So the way to do it is that first you do an element wise multiplication of the input matrix and the prediction matrix. So you multiply 1 by zero point 0.7, 0 by zero point 0.1, and 0 by zero point 0.2. So then it will be 0 0.7, 0, and 0. Then you do an element wise multiplication of the second row. So then it will be 0 into zero point 0.1, which is 0, 1 into zero point 0.5, which is zero point 0.5, and 0. And then you do the same for the third row. So for the third row, it will be 0, 0.9, and 0. Then you sum all the columns, and then it will be zero point 0.7, zero point 0.5, and zero point 0.9. And then you take the negative log. So then it will be negative log zero point 0.7, negative log zero point 0.5, negative log zero point 0.9. So we'll reach exactly the same answer. If the inputs are not one hot encoded, so if the inputs are just if the inputs are like the correct answer is just the 0, 1, and 1. So if these are the correct answers, if 0 corresponds to red, if 1 corresponds to green, so these are the true values, red, green, and green. In this case, we'll just do it index wise. So then we'll look at the predicted answer, and for the first row, we'll take the 0th index, which is zero point 0.7. For the second row, we'll take the first index, so only zero point 0.5 will survive. And for the third row uh, of the predict, we'll take the third index, which is 1. So then zero point 0.9 will survive. And then again, we'll do the negative log of all of these values. So this is how we'll do the forward pass in the loss function. To do the backward pass in the loss function, we will need to find the partial derivative of the loss with respect to the predicted values. And this actually leads to a simple answer, minus true divided by predicted. But I'm not going to go through this right now because it turns out that in actual practice we don't need the backward pass implemented just for the loss function. Very similar to what I told you for the softmax, we'll actually be chaining the softmax and the loss, and then we'll be doing a combined backward pass on both the softmax and the loss. So for the purposes of this practical demonstration, all you need to know is how to do a forward pass on the loss function. Now let me take you through the code of the loss function and show you how the forward pass is calculated. Okay, so in the forward pass of the loss function, we take two inputs, the predicted value and the true value. So very similarly to what I showed here, we take the rather than calling it input, let me call it predicted, or true rather. Okay, so this matrix will be called as the true matrix, and I'll be switching to green color. So this matrix will be called as the true matrix. I'll be reducing the font thickness a bit. Right. So this is the true matrix. So for the forward pass of the loss, we'll be taking in inputs as the predicted matrix and the true matrix. Okay. First thing what we'll be doing in practice is that we'll be clipping both sides to prevent division by zero. So we'll make sure that the predicted values are restricted, or the y-pred is restricted between a very low value and 1 minus 1 into 1 minus 10 raised to minus 7. So y predictions are anyways going to lie between 0 and 1, but we don't want to make them 0 or 1 exactly. So we just make sure that they lie between 10 raised to minus 7 and 1 minus 10 raised to minus 7. Then what we will be doing is that if the labels are one hot encoded, then as I showed you, first we'll be taking the product of the predicted value and the true value, and then we'll be summing the columns. So that's why it says x is equal to 1. So let me take you back here. If the inputs are one hot encoded, we'll take an element wise product and then we'll sum the columns. So to take an element wise product in Python, we just do the this multiplication operation. So we do the element wise product, then we sum along the first axis. So this is if the labels are one hot encoded, or if the true values are one hot encoded, which can be checked by checking their shape, and if the length of their shape is equal to 2. But if the length of their shape is equal to 1, which means that if the true labels are just given as 0, 1, 1, for example, then all we need to do is just we look at that particular index in y true. So what we'll be doing is that if this is how the labels are given, we'll look at the predicted matrix and just look at those index. For example, in the first row we look at the 0th index, for the second row we look at the first index, and in the third row we look at the first index. And this is exactly what is done in this part of the code. We just So this range of samples means the indexes, and just y true means just the 0, 1, 1 what I showed you, and then we'll be looking at these indexes in the predicted matrix. And then in whichever case, if the shape is 1 or if the shape is 2, or rather if the length of the shape is 1 or if the length of the shape is 2, we'll then be taking the negative log of whatever we obtain. So it's this final step where we take the negative log. We'll be taking the negative log of whatever we obtain. So this is the negative log likelihood, which is returned through the forward pass. Remember that when we do the forward pass, for every batch of data, there is going to be one loss. So for example, this first batch has the outputs zero point 0.7, zero point 0.1 and zero point 0.2, and the loss corresponding to the first batch is negative log of zero point 0.7. The second batch has outputs zero point 0.1, zero point 0.5 and zero point 0.4, and the loss corresponding to the second batch is negative log of zero point 0.5, and the third batch has outputs 0.02, zero point 0.9 and 0.08, and the loss corresponding to the third batch is negative log of zero point 0.9. We did not look at the back propagation or the backward pass for the softmax and the loss separately for a very specific reason. It turns out that if you combine the softmax and the loss, there is a very simple formula to find the uh, partial derivative of the loss, with respect to the softmax inputs. If we were to do the loss separately in the backward pass, we would have found the partial derivative of loss with respect to z1. If we were to do the backward pass on the softmax separately, we would have found the partial derivative of softmax output with the softmax input. Now what we will be doing is that we will be finding in one simple formula the partial derivative of loss directly with x1, which is the softmax input, and I'll show you how we can do that. So instead of computing partial derivative of L with respect to Z1 and partial derivative of Z1 with respect to X1 separately, what if there is a simple formula to find partial derivative of L with respect to X1? And it turns out that there is a very simple formula, and that simple formula just turns out to be the prediction minus the ground truth. And this is partial derivative of L with respect to X1, or partial derivative of L with respect to the inputs to the softmax. Let me explain what this means. So let's say we have from one batch of data, let's say we have predictions of Z1, Z2 and Z3 as zero point 0.7, zero point 0.1 and zero point 0.2. These are the predictions. And let's say for that input class, the true value is red, which means that the ground truth is 1, 0 and 0, and we want to find the partial derivative of the loss with respect to x1, x2 and x3, right? So we need to find the partial derivative of loss with respect to x1, partial derivative of loss with respect to x2, and partial derivative of loss with respect to x3. And the simple formula for that is just prediction minus the ground truth. So the prediction is zero point 0.7, zero point 0.1, zero point 0.2, and the ground truth is 1, 0 and 0. So we'll just be doing zero point 0.7, zero point 0.1, zero point 0.2 minus 1, 0, 0, and that is minus zero point 0.3, zero point 0.1 and zero point 0.2. This is the partial derivative of loss with respect to the softmax inputs. That's it. It's as simple as that. And remember that in practice what we'll be doing is that we'll always be dividing the predictions or the partial derivative with the number of samples. So right now this is just for one batch, but later if we do it for 100 batch samples, we'll be dividing each of these by 100. And the reason is because these partial derivatives will be used in gradient computations, right? So if we do not do this division by 100, the gradient just get added for different batches, and that may lead to a huge gradient value, which is sometimes also called as gradient explosion. And we want to prevent gradient explosion, or we want to avoid this, and that's the reason why we always divide uh, these answers or these partial derivatives in this case by the number of samples or the number of the data batches. So this is how we find the partial derivative of loss with respect to the softmax and loss input. So this is called combined softmax and loss. For this forward pass, we have seen the forward pass separately for softmax and the categorical cross entropy. So that remains the same. For the backward pass, we'll just do prediction minus the truth. And now let's see how this is implemented in Python. So this is called combined softmax activation and categorical cross entropy loss for last layer. So the forward pass is just similar. We do the softmax forward pass, and then we just do the loss. We just do the loss function, and then we find the softmax output and the loss function output. That's the forward pass through this combined class. In the backward pass, what we'll be doing is that the main thing which we'll be doing here is that the gradient values are just the, as you can see, the gradient values are the prediction minus the true values. So what we have written here is that calculate gradient range samples comma y true minus equal to 1, which means that we just initially we set the answer to the predicted values, and then we subtract the true values from it. That's it. And then in the last step, what we are going to do is that we are just going to divide by the number of samples. So as you can see, it leads to a very simple formula, and that's the reason why I wanted to combine the loss function with the softmax, and I did not want to do the backward pass separately because ultimately it leads to the same answer. But this is just a much easier formula to understand, and it's a much easier formula to also replicate in practice. One thing which I want to mention here is that the way this code is structured, it just works best if one hot encoded values are converted into discrete values. So there is just a if else statement for this conversion. But the main logic can be found in this part, where we'll be just subtracting uh, predicted minus true, predicted minus ground truth, and we'll be just dividing by the number of samples to prevent gradient explosion. So with this, we have now completed the two steps of this lecture. To everyone who has reached this part, thank you so much for watching up till here. So we have completed the first step on problem description. We have completed the second step on layers, activation and loss. And now we turn to the third step, which is the role of optimizers. So let me come to the third step. So up till now, we have done a forward pass and a backward pass, which means that we are ready and equipped to find the partial derivative of the loss with respect to the weights, biases, and inputs of any layer. And we are also ready to find the partial derivative of the loss with respect to the final layer input. So essentially, we are ready to chain everything together to even back propagate to the first layer and find the partial derivative of loss and bias with respect to the first layer. So we have all the ammunition necessary. Now we just need to find the update rule. So let's say we find the gradient. So let's say we find the, let me switch to a different color. So let's say we have found the partial derivative of the loss with respect to the weights, right? How do we update the weights and how do we update the biases in subsequent iterations? For that, we need optimizers. The simplest optimizer is the vanilla gradient descent, and we can make more and more additions to this. A simple addition is called momentum. Then, when we use adaptive step sizes, it's called RMS prop. And when we combine the momentum plus the adaptive step sizes as in the RMS prop, it leads to the ADAM optimizer. This is the most widely used optimizer in machine learning frameworks. So let's see how each of these optimizers progress from left to right and what are the advantages of the ADAM optimizer. So if you directly use the vanilla gradient descent, it's a very simple formula. You just take the current value of the weights and you subtract the step size multiplied by the partial derivative of loss with respect to those weights. Remember, here we have a fixed step size which is alpha, and only the current gradient value is used. The step size is also shared among all the weights, all the parameters, and only current gradient are used. So for example, if we are at the 50th iteration, only the partial derivative of the loss with the weights at the 50th iteration will be used. We will not take into account what happened for the previous 49 iterations. It turns out that this optimizer is not very good, because if we have a loss function landscape like this, we usually get stuck in local minima and it's very difficult to come out of it. Another problem is that it leads to this oscillation problem. So let's say if this is the loss function landscape and this is the minima which we are trying to reach, and let's say we start from this point over here. If we continuously move in the direction of negative gradient without taking the past into account, it leads to a number of oscillations. These oscillations make convergence very hard. These are the main problems with vanilla gradient descent. An advancement to the vanilla gradient descent is momentum gradient descent. In momentum, what we do is that we take the formula for the simple vanilla gradient descent, which is up till here, but then we add the momentum factor multiplied by the previous weight updates. So here you can see that we are giving a lot of importance to the previous weights. What this will do is that it will cancel out the oscillations. So for example, if you look at this case here and we want to decide where to move at this point, let's say we want to decide where to move at this point over here. Instead of just moving in the direction of negative gradient at this point, what if I take into account the previous gradients and sum them up? If I sum the previous gradients, you will see that some gradients have a left component, some gradients have right component. So if I sum the previous gradients, all the left and right components will cancel each other, right? And then I'll hopefully only the downward direction will survive and I'll proceed towards the minima in a much more smoother manner. That's exactly what momentum is doing. Momentum basically says that the past is important, the past weight updates are important, and we should not neglect them. So this can be expressed in this formula. the current weight is equal to the previous weight minus a step size into beta 1 into the momentum. The So this controls how much weight is given to the past, plus 1 minus beta 1 into the current gradient. So this momentum value is being tracked. So this is beta 1 into the past momentum value plus 1 minus beta 1 into the current gradient. This kind of representation is also sometimes called moving average. So here we can see that the current gradient is not the only important term, but the momentum controls how much importance is actually given to the past weight updates. So it's like giving momentum to a ball rolling down a hill, right? So if the ball is stuck over here in a local minima, when we give momentum by including past gradient updates, hopefully it will get pushed out from here and explore the global minima. That's the main idea behind momentum. But still, when momentum was discovered, people later thought that why is this alpha common across all the parameters? Why are we using a shared alpha? This is a problem, right? Because let's say if the loss function looks something like this. So let's say I have two weights w1 and the loss function looks something like this is the loss function. Look at this loss function carefully. Changes in w1 will not affect this loss function too much because it's divided by 100, but changes in w2 will have 100 times more impact on the loss function. So when we update w2, shouldn't the step sizes be small, and when we update w1, shouldn't the step sizes be large? So this means that if for a parameter the gradient values are small, the step sizes should be large, and if for a parameter the gradient values are large, the step sizes should be small. That way we'll make sure that all the parameters are updating kind of equally, and we don't have some parameters which are not updating at all. This leads to adaptive step size, and this is exactly what is done in the method of RMS prop. So in the RMS prop, if you look at the mathematical formula, the current weight update is the prior weight update minus an effective learning rate. So whatever I'm writing in the bracket right now is an effective learning rate multiplied by the current gradient. So it does not take into account the past gradients for finding this gradient term, but it adapts the step sizes. And for adapting the step sizes, it definitely takes into account the past gradient. In fact, it maintains a term which is called cache. So the cache term, it comes in the denominator, and the cache term is a historical representation of how the gradient square values are accommodating. So very similar to how beta 1 was used in the momentum term, here beta 2 is used in the cache term. Basically, let's look at the current parameter in the let's look at a parameter type w1 in the 50th iteration. What this cache term will do is that it will look at the current gradient square, but it will also look at the all 49 past gradient square values for this parameter. And if this cache value is very high, it effectively means that the gradient values are very high. That's why we should take a smaller step size, and that's why this cache term comes in the denominator. If the gradients are very small, then the cache will be small and this effective step size will be very large. And remember, we could just have taken the present gradient square, but the cache is also like a moving average and it takes into account the previous gradient square for all the previous iterations as well to adapt the step size. So for the adaptive step size, the current gradient does not or matters, but the past also matters a lot. So that's the difference between RMS prop and momentum. In momentum, the step size is not adapted. In RMS prop, the step size changes for each parameter, but this gradient term, this partial derivative of loss with respect to W is fixed. In momentum, this term itself takes into account the past gradients. What Adam does is that Adam says that why don't we use the advantages of momentum and the advantages of RMS prop and combine these two. So what if we use the adaptive step size? So what if we use alpha divided by square root of cache plus epsilon, like which is done in RMS prop, but we also, instead of just using partial derivative of L with W, we'll use the momentum term for updating the gradients. So even for the gradients, we take into account the past, and even for the adaptive step sizes, we take into account the past. For the gradient, the factor which we'll use is beta 1, which controls how important the past is. And for finding the adaptive step sizes in the cache term, the factor will again be beta 2, which is called as cache memory decay rate. So this is the Adam optimizer. One change is done in the Adam optimizer is that the momentum term in the numerator is divided by 1 minus beta 1 raised to t, and in the denominator the cache term is divided by 1 minus beta 2 raised to t. The reason is because at smaller iterations we want the weight updates to start with larger updates. We don't want the weight updates to be very small. So this is around zero point 0.9, let's say. So at t equal to 1, this will be 1 minus zero point 0.9, so this will be multiplied by 10. So this will kind of ensure that we don't succumb to the cold start problem and the weights start updating almost immediately. In practice, the beta 1 value which is typically used is around zero point 0.9, and the beta 2 value which is typically used is around 0.999. And the alpha which I have written here, this is not constant, even this is decaying with time. Usually in practice, this alpha decays as alpha naught divided by 1 plus decay into time, where decay is the decay rate and t is the number of iterations. This makes sure that initially alpha, the step size is large and later it decays. Even this is done to ensure that we don't have the cold start problem and we start taking long steps initially. So this is the Adam optimizer, and now let us see how the Adam optimizer is coded out in Python. So very similar to the other uh, classes like layers, we define a class for this Adam optimizer. This class has essentially four methods. It has the init method, it has the pre-update params, it has the update params, and then finally it has the post-update params. Let me tell you what is happening in each of these methods. In the init method, what we are doing is that we are keeping track of parameters. So beta 1, as I mentioned, controls the momentum history. It's around zero point 0.9. Beta 2 controls the adaptive step size gradient square history, which is cache decay rate. That's 0.99. Epsilon is added in the denominator in the Adam to prevent the denominator from becoming 0. And remember, alpha is alpha naught divided by 1 plus decay into time. So we also have to define what is alpha naught and what is the decay rate. So by default, alpha naught we start out with 0.001, and by default we start out with the decay of 0. These are the parameters which are tracked in the init. This is a method which is called automatically after an instance of the optimizer Adam is created. Then we define the this rule alpha is equal to alpha naught divided by 1 plus decay into time, because remember, even this alpha is changing with the amount of iteration which we are on. And so the current learning rate is just alpha naught divided by 1 plus decay into time. The main update is happening in this update params method. So we are maintaining a separate parameter for the weight momentums, weight cache, bias momentum, and the bias cache. And as I have noted before, the momentum is going to be defined as beta 1 into previous momentum plus 1 minus beta 1 into current gradient. So this is how the weight momentum is defined: beta 1 into previous momentum plus 1 minus beta 1 into current gradient. And this is how for beta 2 it is defined. Sorry, for bias it is defined: beta 1 into bias momentum plus 1 minus beta 1 into gradient with respect to the biases. And remember the correction term which I mentioned: the momentum needs to be corrected by 1 minus beta 1 raised to the iteration count. Similarly, when we update the cache needs to be updated based on this rule: beta 2 into the previous cache plus 1 minus beta 2 into current gradient square. So when we update the cache, it will look like this: beta 2 into the previous cache plus 1 minus beta 2 into the current gradient square. And this will be the same for the weight cache as well as the bias cache. And similar to the correction term which we introduced for the um momentum, the similar correction term needs to be introduced for the cache. We need to divide by 1 plus beta 2 raised to t. So remember, in the denominator we are dividing by 1 minus beta 2 raised to t. So here also we'll be dividing by 1 minus beta 2 raised to t in the code. And then finally we'll just be applying this formula: the current weight equal to prior weight minus alpha into the momentum divided by square root of cache plus epsilon. This is exactly what is done here. The the current weight is equal to the prior weight minus alpha into momentum divided by square root of the cache value plus epsilon. And the same thing is done for the bias. The current bias equal to previous bias minus alpha into the bias divided by, or alpha into momentum divided by square root of bias cache plus epsilon. And then in the last method we'll keep track of the number of iterations. So remember that the alpha term, which is alpha naught divided by 1 plus decay into time, depends on the amount of iteration which we are on. So we definitely need to keep track of the iteration number also as we are proceeding. So up till now we have concluded three steps in this lecture, which is: first step is defining the problem, then understanding the layers, loss, activation functions, and now we also understood and implemented the ADAM optimizer. Now it's time to bring all of this together and to train the neural network. So let's look at the training code for the neural network. Initially, what we'll be doing is that we'll be creating the spiral data, and we are going to be using 100 samples, and there are three classes: red, green, or blue. Okay, then we are going to call the layer dense class. Remember, we defined the layer dense. The first argument here is the number of inputs, and the second argument here is the number of neurons. So I am going to use two inputs, x1 and x2, and there are 64 neurons. Then we are going to chain it with the ReLU activation class, which are the activation function of the first layer. Then we are going to define the second layer, which has 64 inputs, because those are the number of outputs from the previous layer, and it has three outputs, which are the three neurons. And then we are going to chain it to the combined softmax plus the categorical cross entropy loss. And then we are going to define or create an instance of the optimizer class. The alpha naught we are going to set to 0.02, and the decay rate we are going to set to 10 raised to minus 5. And then we'll be running the forward pass and the backward pass. We'll be running 10,000 iterations of the forward pass, and we'll be running 10,000 iterations of the backward pass. So first we call dense one dot forward. This creates the output of the first layer. We pass that output as an input to the ReLU. So then this function leads to the output of the ReLU. The output of the ReLU is passed as an input to the second layer. Dense 2 dot forward calculates the output of the second layer. Then the output of the second layer is passed as an input to the softmax and the categorical cross entropy. So up till this point we have calculated the entire forward pass. In this part of the code we are just printing the epoch number, the accuracy, the loss, and the learning rate, because remember the learning rate depends on the amount of iteration we are on. Remember, epoch is just cycling through the entire data set once. And then we are going to compute the backward pass. So we start from the end. We first look at the combined softmax plus the categorical cross entropy. We find the partial derivative of the loss with respect to the softmax input. Then we will find the partial derivative of the loss with respect to the weights, bias, and input of the second layer. Then we will find the partial derivative of the loss with respect to the ReLU input. And then finally we'll find the partial derivative of the loss with respect to the weights, bias, and the inputs of the first layer. And then we define these four methods in the ADAM optimizer, right? First we will use pre-update params to calculate the current step size, which is alpha naught divided by 1 plus decay into time. Then we will update the parameters in the first layer using the ADAM optimizer. Then we will update the parameters in the second layer using the ADAM optimizer. And then we will update the iteration count. So because the step size depends on the iteration count, that's it. And we'll be running this loop for a period of 10,000 iterations. So I'm just going to run this right now, and we are going to see the output for 10,000 iterations. So I'll just wait for some time and see the output now. Okay, so 10,000 epochs have proceeded, and let's look at the accuracy. So it starts out from 0.39, and as we reach towards 10,000 epochs, we will see that the accuracy has gone up to 0.933 even, and the loss has steadily decreased to 0.151. This is amazing. We have got an accuracy of almost 93% for a data set of 100 samples, and the loss has decreased to 0.151. This clearly means that our neural network is working very, very well. Now you can see that we have just written 14 code cells in Python. We have written the first cell for the dataset and plotting, the third cell for the layer dense activation class, the fourth cell for the ReLU activation class, the sixth cell for softmax, the eighth cell for the loss class, the 10th, the 11th cell for the combined softmax and categorical cross entropy, the next cell for the Adam optimizer, and finally the 14th cell for training the neural network. That's it. Within this much amount of code, we have trained the entire neural network without using PyTorch, without using TensorFlow, without using sci-kit learn. Everything has been done from scratch, and we have obtained an accuracy of 0.94, which is around 93%. I hope this makes neural networks very simplified and easy to you. It's like opening the black box. And I hope you won't find the forward or the backward pass difficult after this. I just want to show you a quick video of the results which we have obtained. So in the video, we have the dots, which are the red, green, and blue data, and then we'll have contours or borders like this. I want you to focus on the contours because those are our prediction values. Okay, so now the prediction has started. This is an animation. Look at the boundaries and look at how they are matching with the underlying data. So I will zoom in a bit here. So the boundaries are our predictions, and you can see that they are also started to look like a spiral, and almost all the data points are correctly classified. There are some data points which are incorrectly classified, but such as, for example, no, in fact, all the data points which I see are almost correctly classified. Even small changes, such as here there is a green border which classifies the green data point. This might be overfitting, but we'll come to testing later. This video is just for the training. So we are able to train the neural network on all of the underlying data, and our predictions match the underlying data very, very well. I just wanted to show you this animation because this is the result of all the hard work which we have put in. I hope you understood the code. If there are some parts which were a bit fast or which were a bit unclear, I highly encourage you to go through the neural network from scratch series, because I have a 30 to 40-minute video for every single section which I just explained to you right now. Thank you so much, and I'll later be making even longer master classes and even shorter master classes for neural networks. I'll see you in the next set of videos.